Assalamu alaikum guys. Today we are going to start our topic, that is impact of jet. We need to start or discuss our case number 7, where we have the scenario of force of jet on series of the moving curved plates. So where theta 1 is equal to 0, and that is going to simulate the half bucket of the Pelton wheel. So for the case when the curved plates are moving, so we need to take the relative velocity in our consideration. So first of all, how to draw the velocity triangles for the moving buckets at the inlet tip and at the outlet tip. So tips to draw the velocity triangle, obviously, we need to see that what is happening when theta 1 is equal to 0. At inlet tip, there is no inclination, there is no vane angle. Then all of the direction are same. The velocity for first we have the velocity of the jet as v1. We need to define, so its direction will be in the forward direction of the bucket, same as of the forward direction of the bucket. And u1 is the displacement of the bucket itself. So the relative velocity will be equal to v1 minus vu, that will be equal to vr1. So if you are going to draw the vectors for u1 and one vector for vr1, then the addition of these two vectors will be equal to the velocity of the jet. And the relative velocity Vr, that will be equal to V1 minus U1. So generically, whatever the scenario is, this is the vector representation of the velocity, where Vr1, the relative velocity vector, will be equal to the vector of the velocity of the jet minus vector of the displacement or velocity of the bucket itself. And similarly, the velocity of the jet will be equal to Vr plus U. So in that way, we can understand well the velocity triangle for the case when theta 1 is equal to 0. But when we have theta 2 having a certain inclination at outlet tip, so we need to see that how we need to justify this relationship. Vr is equal to v minus u, relative velocity is equal to v minus u. For that, we know the velocity of the jet, vr1, relative velocity, will be going to slide through the internal surface of the bucket, and it will just going to become out, okay, as vr2. So the direction of the vr2 will be the same as theta 2, but the velocity of the jet, that will be deviated due to the movement of the bucket in the backward direction. So it is going to be moved backward in the case when it is in the same direction as of the velocity of the jet. So when the jet, actually the physically the water is coming out from the outlet tip, so it will going to be deviate in the backward direction. So the actual water is coming in a deviated form as v2. Its direction, the velocity of the jet will be a jet, actually the water physically been coming in the direction of v2, and the movement of the bucket, according to that, the velocity will be as vr, the relative velocity, this will be same as the direction of theta 2. So we have this v2 velocity that can be just divided into its two component. One will be the vf2 and second will be the vw2. It will be defined as the flow velocity, and vw2 will be defined as the whirl velocity. But first we need to justify the velocity triangle. So we have this vr, okay, 2 is equal to v2 minus u2. So if we have the direction of the relative velocity as same as of the vane angle at outlet tip, so we can draw from E to G the VR2 vector. And if we are going to define the velocity of the jet as v2, that is deviated due to the movement of the bucket in the forward direction, so your direction of v2 vector should be from E to F. Now if we are going to show the direction of the vector, so it will be from E to G for vr2 and from E to F for v2. So we need to just show your u2 in the subtractive form, because we have vr2 is equal to v2 minus u2. So the direction of u2 should be opposite. Okay, so we need to subtract it. So this u2 will be directed in the right direction, in the forward direction, same as the movement of the bucket. So it is going to justify the velocity triangle. So if we are going to draw independently starting from the outlet tip, that is E point, so this should be VR2, we know, and it should be the direction same as vane angle at outlet tip. And your V2 is here as in vector, the velocity of the jet itself. So the velocity of the bucket U2 should be in the is in this direction to justify the relationship that the VR2 is equal to V2 minus U2. So your vectors are subtracting from each other, so direction of the U2 should be from left to right. And finally we can justify it. So if we are going to be see this relationship, so your outer triangle will be justified. Now your theta 2 is this one in this case. So we need to define another angle of the velocity of the jet with the horizontal. This is B2. Okay, and it should be called as or defined as guide plate angle. So beta 2 is the guide plate angle, and that guide plate angle is equal to 0 at inlet, because we have theta 1 is equal to 0, the same direction of V1 and VR1, so there will be the same angle 0. So no guide plate angle will be existing here at inlet, but outlet you need to define the B2 as well, the guide plate angle as well, and the outlet vane angle or vane angle at outlet tip. So we can just resolve our V2 component, the vector, into two of its basic components. That should be the vertical component defined as the velocity of flow, and the horizontal component as the whirl velocity. So this would be those two components, and these components will be calculated, will be determined analytically based on this beta 2. Okay, so your u2 will be equal to gf. We can just have this as h, for example, this point. So h to f we have vw2, the whirl velocity component of v2, and horizontal component of v2, and vertical component will be called as vf2. So from e to h. So in that way we can just draw or justify. Another fact is that your vr2 cos of theta 2 is should be less than u2. Okay, because we are expecting our v2 deviated, the actual jet deviation, backward forward deviation, due to the movement of the plate in the forward direction, in this in deviated backward in that particular direction, and its direction we are not expecting this v2 to be placed, or the jet to be going in this direction. Okay, so we have this vr2 as or that inclination as in reference. So within this range anywhere your v2 must lie. Okay, it should exist. So the range of the v2 is within this quadrant. Okay, it is not going outside vr2 towards this side. So this is happening because this is logical. Our plate is moving in the forward direction, so due to the movement it should deviate in the backward direction, so it is not moving in the other direction. So to satisfy or justify this thing, we need to keep vr2 cos of theta 2 less than u2. Okay, so in that way we can justify the velocity triangle. Now we need to start with our defining our parameters. So we have d as diameter of the jet, we have the a cross section area, q discharge, and so on. v1 is the velocity of the jet at inlet tip, u1 is the velocity of the plate at inlet tip, and this is called as peripheral or tangential velocity, and this can be calculated by pi d1 n by 60. So, and for the peripheral velocity at outlet tip, we have u2 pi d2 n by 60. So we have the case of the Pelton wheel, the peripheral velocity equal to each other, u1 and u2. Okay, so we do not have two different dias at outlet, at inlet. We need to take the average diameter or in the center. So usually what we are going to do, that we have the shaft at the center, and we have wheel, and our buckets or the vanes are mounted at the outer periphery likewise. So we have usually this splitter present in the lateral direction. So here we have splitter, okay, for the Pelton wheel. So we have the inlet and outlet tip situated at the same diameter with respect to center. Okay, so this is the Pelton wheel, half bucket of the Pelton wheel. I told you earlier that what is the situation. We have this splitter present just at the center towards the width, okay, in the lateral direction. So here the water is required to be entered from one side, and laterally it is just gliding through the surface. Okay, so the inlet and outlet tip is going to be having the same diameter. So D1 is equal to D2. Similarly, U1 is equal to U2. And we have radius of inlet outlet tip, it is same, we know. So the relative velocity should be equal to V1 minus U1. Similarly, VR2 should be equal to V2 minus U2. Theta 1 is the main angle and beta 1 is the guide plate angle. And this angle actually is of the jet velocity, and it is 0 degrees at inlet. Similarly, we need to define all of the parameters for the outlet tip, and for that we have this VR2 is equal to V2 minus U2. This should be the vectorial difference. So we can place the vectors as well. This is going to give you the same relationship, and the component of the V2 will be equal to Vf2 and Vw2, where Vw2 is the whirl velocity at outlet tip and Vf2 is the velocity of flow at outlet tip. So here you need to write tip, outlet tip. So this is actually been defined as the component of V2 along x direction, and numerically been calculated as V2 cos of beta 2. And the Vf2 will be defined as the velocity of the flow at outlet tip. It is actually the component of the V2 along y direction, and it is V2 sine of beta 2. Now, continuing to apply the impulse momentum equation along the x direction, sigma fx is equal to m mass flow rate multiplied by the relative velocity change of the relative velocity along the x direction, or the mass flow rate multiplied by the whirl velocity, because the whirl velocity are the component of v1 and v2 in the horizontal direction. So if we are doing our calculation for fn, for the x directional component of the final force, the resultant force or impulse of the jet, force of the jet, so we need the x directional forces. So x directional forces with respect to v2 will be the whirl velocities, and with respect to the relative, it should be the relative velocity, same as VR, delta VR and their x component. So for VR2 as well, we can just resolve this VR2 into its both component. So this will be aligning or coinciding with VF2. Okay, the VR2 will be equal to VF2. That should be the same as the vertical component of V2. And VR2 x cos of theta, that is the x directional component, will be along this direction. So you have the, in terms of relative velocity, VR2x and VR1x, the change of the relative velocities. So we do not have the x component, we all vertical component for VR1, only x theta is equal to 0. So we have this VR1x equal to VR1, and we can just write our expression, simplify our expression as VR1 plus VR2 cos of theta 2, taking and cancelling out this negative, okay, from both sides, and you have Fn is equal to this relationship. And for the real plates, this is for the real plates, but practically our relative velocities are VR2 at outlet tip is less than the relative velocity at inlet due to the friction. So we need to just take these two relative velocities equal to each other. This is equal to V minus U. So you can replace with VR and then V minus U. And finally, this equation number 3 we can derive for the ideal plates. So work done by the series of the moving plates. So you have Fn right now with you. You can multiply it with the velocity of the bucket, and then rho q Vr1 plus Vr2 cos of theta 2 multiplied by u. So you know the derivation for the work done, that is work done per unit weight by dividing it with the gamma q. And you can just simplify your relations by cancelling out the similar terms. The rho and the q will be cancelled out, and you will be left with only this expression as given in equation number 5. And if we have input as v square over 2g, we can input over here, and we can further get our equation number 6 directly to find out the efficiency of the case when your bucket is moving in the forward direction, and the case when your theta 1 is equal to 0. Now, this slide is additionally giving you an alternative way to find Fn, where the whirl velocities, in terms of the whirl velocities, we can find out the normal force component for the resultant. And here you can have this VW2, okay, minus VW1. So we know VW1 is equal to V1. Here we have this whole velocity component, theta is equal to 0. So the cos component is the same as of the actual resultant. So V1 is equal to VW1 for the inlet case. But for the outlet, here we have VW2. So this VW2 can be defined as the U2 minus this G to H. We have defined this point as H. So minus GH. So you can have GF minus GH. Okay, that should be your VW2. So your GF is equal to U2 and GH is equal to the horizontal component of VR2. So as I told you, this is the horizontal component of VR2. So this should be the same as this one. Okay. So VR2 cos of theta 2 is the horizontal component. So that will be shifted over here. Okay. So you can just write your VW2, okay, as GF minus GH, U2 minus VR2 cos of theta 2. And then we have this U2 minus V1, okay, just combined together, and VR2 cos of theta 2 we can write separately. So this U2 minus V1, okay, here we have, and on the other side we have VR2 cos of theta 2. So this can be written by multiplying it with rho q separately, okay, and U2 is equal to U1, we know already, because we have same diameter. It is a splitter for Pelton wheel at the center. So inlet and outlet are just giving you the same diameter. So we have D1 is equal to D2. So U1 is equal to U2. So we can replace our U2 with U1. So it would be V1 minus U1. And we can have this relationship here. So V1 minus U1, it is equal to VR1. We know already this relationship. So VR1 plus VR2 cos of theta 2. This is the same expression we have derived earlier. So up we can do it in relative velocity terms. Then for ideal plates, again the same scenario. We have VR1 is equal to VR2 is equal to VR is equal to V minus U. And finally we may have for ideal case this expression. So we have the Fn finally for ideal plates just highlighted over there. Now, as I told you that while using the change in the whirl velocity concept, we must check our velocity triangle at outlet tip numerically. So VR2 cos of theta 2 should be equal to U2. If that's so, then your velocity triangle is okay. Your bucket is working well. It is moving in the forward direction. Okay. And due to which the jet will be deviated in the backward direction. Okay. So in anywhere its direction might be. So if it is moving, so it might be here. V2. So finally you need to check that your VR2 cos of theta 2 should be less than U2. And if your VR2 cos of theta 2 is greater than U2, mean your V2 is not lying over here. It is anywhere in this region, in this quadrant. So that would be wrong. So you need to satisfy the velocity triangle is incorrect at outlet tip, and you need to correct it. And you need to see that whether this V2 will be lying here, okay, in this quadrant, or till VR2. So anywhere it's need to be deviated. So for FT, tangential component, you have the rho Q delta V R Y, the y directional forces we need to just incorporate. For that, VR2Y minus VR1Y, and VR2Y is minus VR2 sine of theta 2, and as theta is equal to 0, so at inlet tip it should be equal to 0. So we are only left with minus VR2 sine of theta 2. This is for the real case, and for ideal VR2 will be replaced equal to VR1 equal to VR. So we need to incorporate over here for ideal plates. Ft is equal to minus rho q VR sine of theta 2. For resultant, we have fn square plus ft square whole square under root, and alpha is equal to tan inverse ft over fn. Now we can solve the numerical problem number 7 easily, where we have the dia of the jet equal to 75 millimeter, velocity of the jet as 21 meter per second, deflection angle as 120 degrees. From there, theta 2 can be calculated as 180 minus phi. Theta 2 is equal to 60 degrees. Theta 1 is equal to 0 degree. This is the half bucket of the Pelton wheel. You need to find out force when your discharge is equal to 0. And if it and sorry, you need to find out the force of the jet and the discharge where your plate is stationary, it's not moving, u is equal to 0. And you need to find out the force of the jet, normal component of the force of the jet, when the bucket is moving with a velocity 10.5 meter per second. And you need to also to find out in the B case the work done per second and the efficiency. And for the case A, it's relatively easier. Just you need to find out the force and the discharge. Discharge is area into velocity. It comes out to be 0.0927 meter cube per second. And you need to find out the force of the jet. So it should be Fx at first. So do not need to write these. Just directly you can use this equation. If your VR1 and VR2 with the losses information given, friction losses information given, so you need to use, otherwise you can have the concept of the frictionless plate. You need to assume the frictionless plate, and the VR1 is equal to VR2. So the VR1 here, should be equal to V1 minus U1 as the velocity triangle at inlet tip. So we have velocity of the jet 21, we have U1 is equal to 10.5, so we have the VR1 equal to 10.5, and due to frictionless case, this both are equal, and this is same as 10.5. If that's so, then you can input in the equation and you can get your force, okay, as 1460.3 newtons, okay. So if the relative velocity is there, otherwise for the first case there will be no movement, but for the B part you need to find out work done per second, okay. For that, Fn multiplied by U 10.5, and you need to find it out as work done per second as 15330.3 watt. And then the efficiency, output divided by input, is 74.9%. So if your discharge is going to be having lesser value, so obviously there will be more efficiency, okay. So if you are going to reduce the thetas, okay, then again your efficiency will be increased. Now, in the similar way, we can also drive the force of the jet for case number 8. This is the force of the jet on series of the moving curved plate when theta 1 is not equal to 0. So we have the vane angle at inlet tip, we have a vane angle at outlet tip. So at inlet tip, we have defined it, okay, already. This is same as of your case number 7. The velocity triangle, their components, their all points, their vectors at outlet. We are here in this case going to define all of the parameters at inlet tip. For this case, we have the same scenario. If the bucket is going to be move in the forward direction, so due to this movement, a little bit deviation of the jet should be towards from the vane angle towards this side, we may expect, okay. So when it is moving in the forward direction, so little bit your jet will be deviated, the actual jet will be deviated towards the downward side, okay. So VR1 will be same, the direction of the VR1 relative velocity will be the same as the vane angle, but your actual jet will be deviated a little bit downward side due to the movement of the plate. So the velocity of the jet V1 will be deviated, and it should be defined as AB vector. So you have a CB vector as VR1 relative velocity and AB vector as V1 the velocity of the jet. So we know that the angle formed by the velocity of the jet with the horizontal, it should be guide plate angles, and this guide plate angle is equal to beta 1 defined over here. So this is beta 1, okay, and we have the relative velocity vector making an angle of theta 1 with the horizontal. So we have theta 1 and we have theta beta 1, both being defined over here. So we have this theta 1, and now if we have the relative velocity and we have the velocity of the jet. So in a similar manner, the velocity of the jet V1 can be resolved into its two component. One is horizontal component from A to D, that will be defined as the whirl velocity at inlet tip VW1, and the vertical component will be defined as VF1, the flow velocity at inlet. Okay, so in that way we can define our velocities component. And u1, we know that it is the v, that is the total velocity v1, it's a horizontal component vw1 minus the horizontal component, it's from c to d, so that should be u1. So u1 is from a to c, the relative velocity. Okay, so this should be right here. So vw1 u1 should be equal to vw1 whirl velocity, okay, ad minus cd. Okay, and what cd is the horizontal component of vr, relative velocity. C to d is the horizontal component of the relative velocity. So this is going to complete all of the definitions. So you need to define the whirl velocity, that is equal to v1 x v1 cos of beta 1. Okay, and you have the u1 is equal to u2, that is the whirl velocity at inlet tip, and we have to define the flow velocity at inlet tip, and you need to define the whirl velocity at inlet tip and the guide blade angle at inlet tip as well. Similar, you need to define for the outlet tip, okay, and then you can come up with the relationship. So here just the inlet tip whirl velocity horizontal component will be introduced. We have VR1 cos of theta 1 as well. So VR1 cos of theta 1 plus VR2 cos of theta 2 as ideal plate. For the case when we have both of the velocities equal to each other, so we need to have we are taken common from the equation. Cos theta 1 and cos theta 2 is here. If we want to make our fn maximum, we have discussed this in previous cases. So theta 1 should be equal to theta 2 equal to 0, and this should be kept minimum 0 to 15 degrees. So we may have the ideal condition with maximum Fn component, normal component of the force of the jet, that should be 2 rho qvr. Similarly, if we need to find out the efficiency, then the work done per second by turbo turbine, it should be Fn into U, and then you have the per weight, work done per unit weight, and then the efficiency by dividing output with the input. You may have this relationship. So this equation number 7 is going to define the efficiency of the turbine wheel. So the y component, tangential component, similarly we have now VR1 sine of theta 1 as well with us. So for the real plates we have both of the components VR1 and VR2 and thetas as equation in equation number 8. For ideal plates, we have VR1 is equal to VR2 is equal to VR. And then you have the alpha, the final force, and the angle of inclination. Now we can solve the problem number 8. So we have the mass flow rate as 20 kg per second. We have V1 as 25 meter per second. We have U as 12 meter per second. We have beta 1 as 25 degrees. We have theta 1 is required to find out, where if the deflection angle is known, that is 150 degrees. Okay, when deflection angle is 150, we can determine the vane angle at outlet tip theta 2 as 30 degrees. Okay, beta 1 is given as 25 degrees. Okay, you need to find out the normal force component, and you need to find out the power, and where the relationship between VR1 and VR2 mean the losses are given as 20%. So your VR1 will be 80% of VR2. So you need to subtract the 20% head losses. Consider you need to consider 20% head losses, frictional losses. So this relationship is for loss. So it's mean you need to start with the solution. If you need to find out Fn, then we need to determine VR1 and VR2. Okay, because in that case we have both relative velocities. So VR1 and VR2. These both are both components of the relative velocity at inlet and outlet tip should require to be determined. If that's so, then we need to move for VR1 at first. Okay, so for VR1, we have the relationship. We have a certain main angle at both sides. We have relative velocity VR1. We have velocity of the jet as V2. If we go back, I'm drawing it again. So we have VR1 and we have V1. Okay, this is V1 and this is VR1. Okay, we need to determine this VR1. To find out VR1, we need to solve this triangle. Okay, making an angle of theta 1. Okay, so here theta 1 is involved for VR1. Okay, so if that's so, then you have this relationship, okay, for V1 cos of beta 1, and you can have this relationship as VW1 minus U1. Okay, VW1 minus U1 will be equal to the horizontal component of VR. Okay, this one. So to determine VR, we need any one of the component. So for that we have the whirl velocity VW1. We know what whirl velocity is. Whirl velocity is the horizontal component of the velocity of the jet, that is V1 cos of beta 1. So starting from here till here, this total component will be the cos component of V1. Okay, if that's so, then we have this u1 as well. Okay, we have till this point to this point is u1. So if we are going to subtract this v1 cos of beta 1 from u1, so vw1 minus u1, this 10.65 meter per second, that should be the horizontal component of vr1 from here till here. So this is actually this one. Okay, horizontal component, and the vertical component, this vertical one, this is equal to vf1. Okay, that is equal to flow velocity, and it is equal to v1 sine of beta 1. So if you are going to solve this triangle for vr, so we need two of its components, so that we can find out the square of these two components and then add, and then taking square root we can find out resultant as vr1. So to solve this smaller triangle, we need the horizontal component of VR1, we need the vertical component of VR1, and then we can just take the from the component the resultant as VR1. Okay, so we do not have theta 1 with us, okay, at initial. So we need to solve it numerically by taking the two components horizontal and vertical to find out VR1. And that's way you can solve this triangle at inlet tip, and you can find out VR1. Now we can determine theta 1 as tan inverse of Vf1 divided by V1 W1 minus U1. And I told you earlier this VW1 minus U1 is equal to the horizontal component of the smaller triangle. Okay, so that is the vertical component of VR1. This is horizontal component of VR1. And by dividing these two and taking tan inverse, we can find out theta 1. Okay, that is equal to 44.6. I can draw it again so that it will be understandable to you. A smaller triangle only. So we have VR1 and it is making an angle of theta. This is theta. theta 1. Okay, so this horizontal component is equal to this, and this vertical component is equal to this. So tan inverse equal to vertical to horizontal will be your theta 1. Now you can compute VR2, okay, directly from VR1, because we have this relationship as the frictional losses. So we can have this reduced 12 meter per second relative velocity at outlet tip. Now we have Fn equation directly with us. Just input your values. We have theta 1 now. We have theta 2 given. VR2 and VR1 we have calculated. Just input and get the Fn as 421.2. The power will be Fn multiplied by U, and the output power will be divided by gamma Q, and input is V square over 2G, and efficiency is equal to 80.8%. Then we will discuss the case number 9. That is very simple, where force on a reducer or diffuser you need to determine. What diffuser and reducers are, these are the fittings, okay, plumbing fittings required to change the diameter of the pipe gradually. Reducers are to be used to change from larger to smaller diameter of the pipe, and the diffusers are used to change from smaller to larger diameter. It depends upon the direction of the velocity. In this case, when this diagram is shown here, we have the direction of the velocity from left to right. So it's mean that this is just giving you the pipe diameter is reducing from cross section 1 to cross section 2, and this internal pipe fitting is used to reduce the diameter of the pipe. Okay, so this will be called as reducer. If the direction of flow will be opposite, okay, so the same plumbing fitting will be called as diffuser, that from taking the water or liquids within the pipe from the larger smaller diameter to larger, so it should be diffuser. So the same pipe fitting, depending upon the direction of the flow from larger to smaller, smaller to larger side, it can be defined as reducer or diffuser. So we have a certain force that been applied as the pressure multiplied by area on cross section 1, and we can define the force as P2 into A2 that been applied by the liquid on section number 2. So we have diameter D1 in at cross section 1, and we have diameter D2 at cross section 2. So the velocity of the direction of the velocity in this way, and the force that being be applied by the liquid on the reducer, okay, that pipe fitting, that should be the force of the liquid in the opposite, equal and opposite direction. So that should be the F, and that F is required to determine as force of the water, the liquid that been applied on the diffuser or the reducer during the movement or the flow of the liquid in the direction from cross section 1 to cross section 2. This figure is just to make you aware of different type of the plumbing fittings. For example, we might use the cross fittings where the four sides pipes diameter can be crossed with each other. We can use the three sides, okay, and we have the elbows as plumbing fittings where the bend can be given as the 90 degrees. We may have these reducers practically available in the market. As in pipe fitting, we have long radius benders as well. So at any angle, we can bend our pipes, and we can reduce the diameter or increase the diameter. These kinds of the valves are also used, and we have these kind of the fittings where the elbows are used, where the smaller diametric pipe at one side will be bent at 90 degree on the other side. So we have this larger diameter on the other. So depending upon our requirement, we can go to the market and we can ask for these type of the fittings, and we can use for the pipe. So if we want to find out the force on a reducer or diffuser, so we can define the parameters as D1 dia, A1 cross sectional area, Z1 the elevation, P1 is the pressure acting in section 1, P1 over gamma is the pressure head, V1 is the velocity, and V1 square over 2G is the velocity head at section 1. So if we need to define the parameters for cross section 2, the same are there. HL will be the head loss between section 1 and section 2. So if we need to find out the impulse momentum equation, we can apply for the force of the water on the bender or reducer. So we have this rho q, sigma fx is equal to rho q v2 x minus v1. So we have all of the forces being applied at cross section 1. We have P1 into A1 in the direction that is positive, and P2 A2 is from cross section 2 to the other side, so that should be minus, and the resultant force will also be applied in the minus direction. So we have P1 A1 minus P2 A2 minus F. Another side just V2 minus V1. So V2 will be the velocity at cross section 1. We have these two cross sections. So we have the reducer. We have the smaller diameter pipe. So here we can define the velocity as V1 cross section 1, and here at cross section 2 we can define the velocity as V2. Okay. So we may have this relationship. Okay, the term P1A1 minus P2A2 is due to the pressure in reducer, and the term rho QV1 minus V2 is due to the velocity of the fluid. If we put a valve at the end, then the velocity of the fluid will be zero if you are going to reduce the discharge and then putting it equal to zero. If you're going to close the valve within the pipe anywhere towards upstream or downstream side, then there will be no velocities, but the pressures will always be there. अगर already एक flow हो रहा है आपका pipe के अंदर, ये आपको ये बता रहा है, ठीक है? Once there will be a flow in a pipe, okay, and then during the flowing condition, once that's been initiated, and then at of a sudden you are going to just close the valve properly and making discharge equal to zero, then your velocities will be equal to zero. In equation number 1, that term will be equal to zero, but still you are getting the force exerted on the reducer due to the pressures available in the system. Okay, so that will be eliminated, but pressure can't be zero in any case, rather than when no fluid is present in it. So static pressures will always be there, static heads will always be there, so you can have the velocities equal to zero. So now you can solve the problem for the reducer, where you have dia larger as 0.9 meters, you have smaller dia of the pipe as 0.6. The pressures at section 1 is 414 kilonewton per meter. Velocity is 2.1 meter per second, and you need to determine the force, where head loss is 1.5 meter. You know very well about this strategy. You need to determine the velocity V2 by applying the continuity equation. Then the energy equation can be used to determine the other unknowns, as the P2 pressure, P2 is unknown, P1 is given, P2 was unknown. So you can use the energy equation to determine P2, and then you can apply the impulse momentum equation to determine your force. Okay, that is 150 kilonewton in this case. Force on a reducer bend. Okay, similarly, if the bend will be there, then you have to see that in which plane that bend is there. We can consider the horizontal plane, where the elevations are equal to equal to both are equal. So if we are going to draw the plan view, then we have one side the larger diameter at cross section 1. Then after bending the pipe in the other direction, we have the diameter equal to D2. Similarly, we have P1 into A1 at applied force in at cross section 1, and then P2 A2 in at cross section 2. But this P2 A2 now need to be taken as of its component. Okay, equal to angle of the bend equal to alpha. Okay, the bend angle is equal to alpha. So with the horizontal, if we are going to consider your section number 1 as an horizontal, so this bend is making an angle alpha. Okay, this angle phi, this is the deflection angle, and with the horizontal the force is making inclination angle as alpha. So this phi is the angle, and this is the, with the horizontal we have this angle of inclination alpha. So we can have this P2A2 cos component, we have P2A2 sine component. Okay, and in our derivation we need to incorporate their components. Similarly for velocity, here we have only V1, but for V2, this should be the direction of V2, and there should be the two components, the V2 cos of theta, V2 sine of theta. Similarly, their direction and their symbols. So you can define the parameters, and then you can apply the impulse momentum equation. So I told you for the second cross section 2, you need to input the respective components of the velocity and for the pressures, for the forces, pressure forces. And then you can just simplify and find out the y directional forces as well. Finally, you have x and y, and the final resultant force will be calculated by taking square root of both of the components, square and then square root, adding both and then square root. Resultant and the angle of inclination from the y and the x component can be determined. Similarly, we can solve our numerical problem number 10, where the deflection angle for the bend is given as 60 degrees and P1 is given as 170 kilonewton per meter square. Dias of the pipe are given. You need to find out the force and the angle of inclination when your discharge is equal to 0. The valve is fully closed. And you need to find out the force and the angle of inclination when your discharge is equal to 0.85 meter cube per second. Okay, so you have a certain discharge flowing through the pipe. So for that, the solution is given. You need to just follow the same situation. When your discharge is equal to 0, you have no velocity. So all of the velocity related parameters will become equal to 0, but rest should be there. You have P1, you have to find out P2. Okay, both are equal to each other because situation is not varying, velocity is not varying, it is 0. So you have same pressure at both of the cross sections equal to 170. Just input and you are getting your answer as 42.1 kilonewtons. Now, if you have a certain component, y component to be determined, so in the similar manner, you can determine the y component, it comes out to be 10.4. And then the final resultant and angle of inclination, alpha can be determined. Similarly, if you have discharge 0.85, then you need to apply the continuity equation to find out V1 and V2. You need to apply the energy equation to find out the P2. P1 was given, but P2 is not there. If HL is given in the statement, in the problem statement is okay. If not, then you can assume head loss equal to 0 and you can find out your pressures. If your parameters are will be known, you can find out the x component, you can find out the y component, you can find out the resultant force, and you can find out angle of inclination. So in that way, in a very simple way, you can determine your unknown parameters.